Problem 17. I have a list of 10 normal faults, and the question wants me to find the orientation of the principal stresses, which means to find the trend and plunge of the sigma 1, sigma 2, and sigma 3. The information that I have is the strike of the faults, dip of the faults, and the rake of the Slicken line, or pitch of the Slicken lines. So let's plot first the fault 1, and then we discuss how we can tackle this problem. So this is my Stereonet. And I will start placing my fault traces. The first fault has a 45 degree of azimuth, okay, from north 10, 20, 30, 40, 45, and is dipping towards south 61 degrees, which means this is my strike of the fault and is dipping to that direction 61 degrees. So rotate vellum paper and place the strike of the fault along the north-south line and count 61 degrees along the east-west line. 10, 20, 30, 40, 50, 60, and this is 61. Okay, so the pitch of the Slicken line is 80 degrees from east. This is east, 80 degrees from this end of the fault along the fault trace. So I cannot count like it is. I should rotate my vellum paper and place again the trace of the fault along the great circle as the way that we draw the trace. And now we are able to count 80 degrees from east, right? From this end, you go 80 degrees along the fault plane and you will end up to this point. This is the rake of the Slicken line, and it's better you show the movement of the hanging wall, or the movement on the fault plane, with the small arrow, and you can actually place your ruler and place it on the center of the Stereonet and your rake, and then draw a small arrow like this, and because it's normal fault, it's gonna point out towards the primitive circle. If it was the reverse fault, you could draw this arrow towards the center of the Stereonet. Or if you want to make it easy, after finding your rake, just rotate your vellum paper and place it on the west-east line, and then use the west-east line as a ruler, okay, to draw this small vector. So I have the first fault, and I think it's easier we investigate the principal stress directions one by one, because if you have 10 faults here, it's going to be very difficult to manage it. So what I'm going to do, I will find the sigma 1 and sigma 2 and sigma 3 for each fault separately, and then we can discuss how we come up with the best representative sigmas. I will show the sigma 1 with the red color and red dot, and sigma 2 with the triangle, black triangle, and sigma 3 with the blue quadrants. Okay, so for this fault, I know the sigma 2 should place along the fault plane, right? And 90 degrees off from the Slicken line. So let's rotate this one along the northwest. You count 90 degrees on the fault plane, on the trace of the fault, and you place your sigma 2. So it doesn't matter you go this direction or the other direction around, you will end up at the same point. I will go to this direction. This is 10, 20, 30, 40, 50, 60, 70, 80, 90. So this is my sigma 2 for this fault. And as you noticed, this one was 80 degrees, right? We counted for Slicken light. This is 80 degrees. Another 10 from the other end, you will end up to the same point. Okay, this is sigma 2. I don't want to write the name there because I have my index in the corner. This is sigma 2. And I have my sigma 2. I have my Slicken line. And I have the pole of the fault, right? This is the minimum information that you have up to now. So the pole of the fault, 90 degrees off from this profile, right? So this is 10, 20, 29 degrees, 39, 49, 59, 69, 79, 89, and 1 degree here is 90, right? This is the pole of the fault. So another golden rule, which was if I have the pole of the fault and the Slicken line, I can place these two along a great circle, and that great circle indeed is called the movement plane, right? Let's do that. I will place these two along one great circle. You see the P is here and the pole and the rake is here, right? So if I trace this plane, okay, this plane is called the movement plane, okay? And why is important? Because the sigma 1 and sigma 3 will locate along this trace 45 degrees off from the pole of the fault. So if I have the P here, the pole of the fault, 40 degrees off, 45 degrees off, this is, let's say, 10, 20, 30, 40, 45. One point is here, and the other 45 degrees, either you can count from that direction, or you count 45 or 90 degrees from this towards that direction. Maybe it's easy, I count from the pole, 10, 20, 30, 40, 42, 44, 45. Another point is here. Okay, 1 point here, 1 point here. Each one of them is 45 degrees, okay, off from the pole of the fault. As we discussed in problem 16, okay, in the normal faults, the sigma 1 is perpendicular to the Earth's surface, right, or horizon. So if I have a sigma 1 like that, if I want to show it in a Stereonet, it should be exactly in the center, right, because it's perpendicular to the horizon. So now I have this point and that point. One of them is sigma 1 and the other one is sigma 3. Because I'm facing with the normal faults, the one which is closer to the center indeed is sigma 1. So this one is sigma 1, this one is sigma 3. So what I do, I will put this one here as a sigma 1 and the other one, okay, as a sigma 3. And this one is sigma 3. Okay, for fault 1, now I have 3 points, sigma 1, sigma 2, and sigma 3. I will do the same for all 10 faults, and then I will show you how we can find the best representative point for sigma 1, 2, and 3, because we're going to have 10 sigma 1 point and 10 sigma 2 and 10 sigma 3 points on the Stereonet, and 1 is the best representative for each. I will stop my video here. I will draw the rest and I will come back with the completed version of my Stereonet. Let's look at the third fault. It seems a little bit tricky. The strike of the fault is 90 degrees. Okay, this is the strike of the fault, and it's dipping towards north 80 degrees. This is the fault trace. And the rake of the Sleeken line is 58 degrees from west. From the western end, okay, you go 58 degrees along the fault trace. What I did, it was I placed the strike of the fault along the north-south, and I count from the western end 58 degrees, 10 to 30, 40, 50, 58. You have this one, and you place the arrow. That's fine. You find the pole of the fault. Okay, this is my fault. The pole is this one. And then I have the pitch of this Sleeken line and the pole. I place these two along one great circle somewhere here. See, this is like 10, 20, 32 degrees, and here it's about that size, right? It's 10, 20, 30, maybe a little bit like that. Yeah. Now I can imagine there's a fault trace here. This time I didn't draw it, but I see my movement plane, or the trace, is between the great circle 30 degrees and the great circle 32. Okay, my line is sitting here, so I will use the great circle to count 45 degrees from the pole. I did that. 45 degrees from the pole along this great circle, it's gonna be placed here, and 45 degrees in the other direction, which I will end up here. So this one, it's a little bit, if you think it's a little bit difficult for you, okay, which one is closer, if you cannot distinguish, visually what I did, I placed this point along the east-west line, okay, and I counted the angle 10, 20, 30, 40, 44 degrees, and the other one is indeed 10, 20, 30, 40, 50, 64 degrees. So the one which is closer to the center is this point. So this one, it should be sigma 1, because we are dealing with the normal faults, and the other one will be sigma 3. Okay, I don't want to write it. Okay, here is my all 10 faults. Sigma 1 axis is located here. Sigma 2 is here and there, and sigma 3, 4 points here and 6 points there. So the question now is, as you have seen in the question, right? It says the 10 faults are not enough to get a good result. That's why if we have more faults and more information, we're gonna have a better image. But let's see how we can come up with a good estimation only based on this data. I think if you see more concentration or more density in, for instance, let's say we're looking for only sigma 1s, there is more density here than here, right? The more denser area is here, and then it's here, and then here, because we have like 3 points here and 3 individual points here. For sigma 2 also is the same. It's a little bit difficult maybe to distinguish, just by looking at, but let's see, what about sigma 2s? The sigma 2, okay, we have 4, another 3 here, 7, 2 here, 9, probably I forgot to plot one of them. But what you see here, indeed, you see more concentration of sigma 2 somewhere here. So I would indeed draw kind of circle somewhere here and say this is the best representative location or attitude for sigma 2s, right? So let's say this is just what I'm drawing. It's just based on estimations, but sigma 2 should place somewhere here, something like that. Okay, and we know let's say I have only one representative of sigma 2 and the profile for that pole, because the sigma 2 is the pole of the profile sigma 1 and 3. So if I have this pole, I can draw a profile 90 degrees off from that pole, and sigma 1 and 3 should actually locate along that. So let's place this one like that. What we are doing is just giving an estimation of the sigma 1, 2, 3 location. Okay, so here it's about, let's say, about 10 degrees, and from here about 10 degrees I can actually draw a circle, a great circle, something like that, and the best representative for sigma 1 and 3 should be somewhere close to this profile. So I'm just trying to draw some lines like a density, like a contour lines, which shows the density of the points. Normally this can be done by the software, but we just wanted to come up with the best guess that we can. So for me, I would probably I can draw a line something like that and say my sigma 1 attitude is changing somewhere in this zone, and I see there is a more concentration point somewhere here rather than here or here, right? Because the pole, the sigma 2, which is the pole of sigma 1 and 3 surface, is crossing this point and that point. That's why I want to put more weight here, okay, rather than the other places like that. Okay, let's say this is line, let's say this is 3, this is the value of the contours that I'm putting here. That's why the sigma 1 most likely is suitable to see it somewhere here. And the 90 degrees off along these trays, it should be indeed the sigma 2 location. And as you see, we have some here and some there, and I think the best one, probably the best representative, might be something like that. So let's show the distribution of the sigma 2s, something like that, right? So I would probably go with something like this. Okay, we will practice this example with the software, and you will find out how you can deal with this kind of interpretation. If I want to give one representative of the sigma 1, I would take this point as a representative, because it's a kind of average, it's the best average or best representative that I can have based on these 10 points. And I know somewhere here, let's put this one along the north-south, and you go about 90 degrees. Okay, let's say this in 10, 20, 30, 40, 50, 60, 70, 80, 90, and somewhere here, okay, as a representative of sigma 2, I'm sorry, sigma 3, this one sigma 1, and somewhere here, okay, as a sigma 2. Okay, if I want to write the attitude of the sigma 1, what I do, I take a ruler and I place it like this from center to the densely populated zone, and indeed this one, okay, it's showing the trend of the, okay, this is the trend of sigma 1, and as you see, okay, it's, if I read the azimuth of the sigma 1, it's gonna be 90 degrees, 100, 110, 120, 130, 140, 150, 160, right? So I'm gonna write here 160 slash, what about the plunge? You place it along the east-west line, and it's about 70 degrees, right? Okay, and here 70 degrees. For sigma 2, it's the same thing. It's almost 45, and the plunge is about 10 degrees. And for sigma 3, okay, for the sigma 3, we are somewhere here, 270, 80, 90, 300, 210, 316, and the plunge is about, let's say, 16 degrees. Okay, I have 3 representative plunge and trends, which showing, you know, the best average number for my sigma 1, 2, and 3.